In the silent depths of a specially conditioned chamber, where temperatures barely hover above the absolute zero mark, lies a marvel of modern technology, a quantum computer. Beyond the hubbub and excitement that surrounds it, this piece of groundbreaking technology harbors the potential to redefine our future, promising computing prowess that is leagues ahead of contemporary machines. But to call them the successors of the modern supercomputer would be a vast understatement. They're a breed apart, a force that is set to redefine our computational boundaries. Before we delve deep into the fascinating applications that lie in the waiting, it's vital to grasp the underlying principles of quantum mechanics that fuel the essence of quantum computing. Prepare yourself to journey into a realm far smaller and enigmatic than anything within the bounds of conventional understanding: the mystical world of subatomic particles. Back in the 80s, the pursuit of unraveling the secrets of the quantum universe led Richard Feynman, one of the foremost physicists of the last century, to a significant hindrance. Traditional computational systems faltered, unable to keep up with the intricate complexity of quantum calculations, which surged exponentially with the inclusion of more particles in the quantum models he was experimenting with. But this setback fueled a groundbreaking revelation. Imagine crafting a tool that embodies quantum elements, operating based on the very principles of quantum physics. This tool wouldn't just be capable of exploring the quantum domain, but would bridge the gap between the realms of quantum physics and computer science. Thus, the concept of the quantum computer germinated, setting the stage for a harmonious marriage between quantum physics and computational science. Now, if we aim to comprehend the intricacies of quantum computing, we first need to demystify the very element that forms its cornerstone, the concept known as amplitudes. In classical probability, determining the likelihood of flipping tails on a coin 20 times is a straightforward process, adding up probabilities of all possible outcomes that result in tails. It's intuitive, grounded in common sense. However, quantum mechanics tosses this common sense out the window. Before a subatomic particle is measured, it embodies a wave of probabilities, inhabiting a quantum system that harbors myriad possibilities. This shift in probabilistic rules forms the bedrock of quantum computing, introducing a world where amplitudes, not probabilities, dictate outcomes. These amplitudes are complex numbers, showcasing behavior starkly different from classical probabilities, bringing forth outcomes that can sometimes be utterly counterintuitive. Are you riveted by this quantum adventure so far? If yes, don't forget to subscribe to our Quantum Intelligence channel for more deep dives into the fascinating world of quantum mechanics. In this quantum narrative, the qubit emerges as the protagonist. It stands as the fundamental unit of computation in a quantum computer, akin to bits in a classical machine, but with a twist. Qubits embrace the quantum logic, allowing them to be not just 0 or 1 but a linear combination of both. This fluidity, a harmony of amplitudes, forms the nucleus of quantum computing. Before measurement, a qubit dwells in a state of superposition, embodying both 0 and 1 in a dynamic dance of possibilities. This ability to hold and manipulate a gargantuan amount of data compared to classical computers comes from this unique property of qubits. As we venture further, we encounter another marvel of quantum mechanics: entanglement. In this state of superposition, qubits form an intimate connection, resulting in outcomes that are intricately intertwined, presenting correlations that are alien to the classical world we are familiar with. Envision it as a book where individual pages make no sense in isolation, but when observed collectively, they reveal a profound story. However, representing these highly entangled states using ordinary bits can be a Herculean task, demanding an astronomical amount of data storage. This ability to harness vast computational power was precisely what Feynman implied when he remarked on the inability of classical computers to simulate quantum mechanics effectively. But to extract meaningful data from a quantum computer, one must measure the information from the qubits, which unfortunately leads to the collapse of the quantum system into a classical state. The challenge then lies in retrieving an answer that isn't a random manifestation of probability. This is where interference comes into play. a phenomenon witnessed even in classical physics when waves interact, canceling or amplifying each other. By harnessing interference through a series of qubit gates, scientists can increase the likelihood of obtaining correct answers, concentrating all the amplitudes constructively. It forms the crux of quantum algorithms, a field which has witnessed significant advancements since 1994, promising applications in areas like cybersecurity and search optimization. As we dwell deeper into the realm of quantum computing, it's essential to touch upon the theory of quantum supremacy. It is a significant milestone where a quantum computer performs a task that is virtually impossible for a classical computer to replicate within a reasonable timeframe. This achievement would signify not only a triumph of science, but a testament to human ingenuity and innovation. It is the dawn of a new epoch, where computational boundaries are expanded, fostering advancements in fields such as cryptography, material science, and drug discovery. The quantum computer is not just an upgrade, it represents a revolution, a paradigm shift in how we perceive and utilize computing power in our pursuit of knowledge and innovation. Yet, the true potential of quantum computers lies in their ability to explore the depths of our universe, fulfilling the curiosity that sparked their inception. As we stand on the cusp of a new era, the excitement is palpable, albeit with an element of uncertainty regarding their immediate practical applications. The quantum computer remains a beacon of hope, promising discoveries and applications that we might not yet envision. We find ourselves at a juncture where the promise of quantum computing is not just about solving complex problems, but venturing into the unknown, seeking answers to questions we haven't yet posed. It's more than just a tool. It's a gateway to unraveling the deepest mysteries of our cosmos. As the world stands on the threshold of this quantum era, it is crucial to address the potential challenges that lie ahead. While the prospects of quantum computing are staggering, it is a double-edged sword. The very features that grant it unimaginable power, such as its ability to crack encryption algorithms currently deemed secure, also pose significant security risks. The quantum revolution beckons a rethinking of cybersecurity strategies to protect sensitive information from potential breaches. Moreover, as we transition into this new era, there is an imperative need to foster a collaborative approach, uniting experts from diverse fields to navigate the complex and fascinating quantum landscape that lies ahead. A voyage into the quantum future is not a solitary one. It calls for a global community working in unison, fueled by curiosity and guided by the quest for knowledge and understanding. In conclusion, we stand before the precipice of a new frontier, one teeming with potential and promise. If you enjoyed this expedition into the world of quantum mechanics, do like this video and subscribe to Quantum Intelligence for more riveting content. Together, let's venture into the future, one quantum leap at a time.